Morning, everyone. Welcome back to the cycle of seminars of the astronomy department. This is an extra seminar because this week we have Professor Laurent here with us today. And Professor Laurent Loinard is a professor of astrophysics at UNAM in Mexico. And he's a part of the EHT collaboration, the Event Horizon Telescope collaboration. And he's actually, as of now, the chair of the Calibration group. And he's going to talk to us about his talk is Event Horizon Images of the Black Holes at the centers of M87 and Sagittarius A star. So all the questions you can direct to our speaker after the talk. And I will ask everybody on Google Meet to please turn off your microphones and cameras. And Professor Laurent, you can go ahead.
Okay, thank you. Thank you very much. Everything okay? So thank you very much, everyone, for being here and for having me. Thank you, Renaldo, for organizing the visit. Always a very, very beautiful place. A little bit hot for my taste, but very beautiful place. So what I want to tell you about today is are these images that were obtained with the Event Horizon Telescope. And in particular, what I want to try to do is to explain what these images mean and why they are important. So as was just said, I'm a professor at the National University of Mexico in Morelia, Michoacan, and I am also a member of the Event Horizon Telescope, where I currently chair the Calibration and Error Analysis Working Group. So my talk is really going to be about two black holes. In fact, I'm going to mostly focus on one, on 87. So here's a very nice animation that was made by ESO just before the publication of these first results. So what we are going to do now is to zoom in on M87. M87 is in the cluster of Virgo. This is actually a nice recent image obtained at very low frequency in the radio. And as we zoom in to the center of this galaxy, we see that it's a fairly large galaxy. It's a giant elliptical galaxy. And from the center, there's this jet coming out that was actually recognized very, very early in 2019, I believe, by an American astronomer. And as you zoom in towards the center, you see this very powerful jet. And the image that we obtained with the EHT is the image of this black hole at the center of M87. I'm going to spend a lot of time on this black hole. And then the other image that I published just last year is the image of the black hole at the center of our own Milky Way in the Sagittarius constellation. So now as we zoom in towards that source, we go through the entire disk of the Milky Way, which actually makes a big difference in terms of interpreting the data. And then as we go to the center, we get to these radio sources near the center of the Milky Way called Sagittarius A in general. And one of them, Sagittarius A star, marks the exact center of our Milky Way, the dynamical center of the Milky Way. And this is the image that was obtained with the Event Horizon Telescope. So it turns out, just before we start, and that's pretty much all I will say about Sag A star, really. So those are the two, before I get to this, these are the two images. This one published in 2019 and 2021, the polarization part. And in fact, last week, the second part of the polarization, I will speak to that a little bit at the end of the talk. And this is the image of Sag A star. It was observed for M87 in 4 different days during April 2017. And you can see the images reconstructed for each day. And they are very similar. 2019, it was also observed for several days, although these images are not actually the images for each day. They are representation of different kind of images that we get from this data. As you can see, most of these images also contain a ring. When the M87 results were published, I was the chair of the publication committee, so I was in touch with the editor at Astrophysical Journal when these results were published. And I was very surprised because the editor told me at some point that, yeah, it was very nice, these images, you know. But what was really impressive was that we got the Google Doodle with the black hole on the day of the publication, and we came out in some of these cartoons that are very famous in the astronomical community. He thought that was much more impressive than the image. I didn't quite agree with him, but that was what he said. One thing that I want to say before I start trying to explain what these images mean is, of course, M87 and Sgr are fairly different black holes. M87 is a very large black hole, one of the largest black holes known, with a mass of about 6.5 10 to the 9 solar masses. Whereas Sgr is a much smaller black hole by these standards, only about 4 billion solar masses. So there's about a factor of 2,000 of difference in the mass between these two black holes. But it turns out that M87 is also about 2,000 times farther from us than Sgr. And so the radius, the short-shift radius in angular scale is just about the same size, about 50 microarcseconds. That's coincidence, right? There's nothing fundamental about this, but it turns out that this is such that the two black holes appear just about the same size on the sky. So this is another animation from ESO showing this, right? The size on the sky is the same, but one is about 2,000 times further from it than the other. What is noticeable, or what is remarkable about the size is this size, about 50 microarcseconds. So microarcseconds is a very small number. 50 microarcseconds corresponds just about the size of a single atom seen from 1 meter. So if I had eyes that would allow me to see these images, then I could see a single atom in my hand seen from my eyes. This is about the size. So this is the difficulty about making these images, is getting an image that has enough resolution that it would be able to see a single atom at 1 meter. So what telescope can do that? Well, there's only one really, and it's this telescope that gave the name to the entire project, the Human Horizon Telescope. And it's a telescope that's basically the size of the Earth. So I really don't want to enter into the details of exactly how that works. If you have questions, I'm happy to answer them. But basically what we do is we use interferometry. So instead of using a single telescope, we use about a dozen different telescopes distributed over the entire globe, from the North Pole or Greenland to the South Pole, and from Hawaii to Europe. And these telescopes are all pointing at the same source at the same time. They are measuring what are called visibilities, which are components of the Fourier transform of the image. And then we reconstruct the image from these visibilities. So it's not a direct imaging telescope. It measures quantities that can then be transformed into an image under certain conditions. So that requires a lot of people. This is a photo that was taken in 2018, precisely in the EHT meeting when we were working on the very first papers. We were in Nijmegen in Holland, and that's a small, maybe about half of the collaboration right there. And one important thing is that the reason we are so many people is multiple. There's a lot of different expertise that are needed to make these images. So you need people, you need astronomers, right? You need observers at the telescope when you observe. Then you need people who know how to build the kind of electronics, microelectronics that is needed to make these observations. So for instance, this gentleman here, no, I saw him a minute ago, but I lost him now. Oh, here. This person here is a very well-known specialist of this kind of microelectronics developments. Then you need people to do the correlation, to mix this signal. You need people to calibrate this data. This is what I'm doing now as part of the calibration working group. You need specialists of transforming these images, these data into images. You need physicists who can then make models that we can compare with the results. We need mathematicians. We need all kinds of people. Right? So the reason we are so many, about the last count, I think we are almost 400, is because we need all of these kind of expertise. So I'm really not going to enter into the details of exactly how the images are done. What I do want to speak about is what these images mean. Right? So again, these are the two images of the two black holes. I'm really going to focus mostly on M87 just because we have more data that have been published. The data are somewhat easier to analyze because in the case of Sgr, as I said, you have to go through the entire galactic disk before you get from here to Sagittarius star. There's material along the galactic disk. Some of it doesn't really matter, like dust. The wavelengths we are using are more or less transparent at those wavelengths. But it turns out ionized gas does produce an effect on the radiation that comes from the galactic center that has to be taken into account, and it just complicates the analysis. So I'm really going to mostly focus on this image. And the first part of the talk, what I want to explain is why the image looks like this. Why do we get this image and not any other image? And why this is what we expected to, why this is what we expected. So to explain this, I need to spend a little bit of time. Is it too strong or? It's fine. I need to spend a little bit of time talking about general relativity. So, as we know, general relativity is the modern version of gravitation. It replaces Newtonian gravity when gravity is particularly intense. And the way that general relativity describes gravity is, instead of using the concept of forces that appears in Newton's description, the way that gravity is explained in general relativity is when you put a massive body somewhere in space, that body will have an effect on the surrounding space and time. So it will curve space-time in its surrounding in such a way that if you then bring another body close to that first body, it will follow a certain trajectory that will be dictated by the perturbation of, say, space-time created by the first body. And one of the main differences between general relativity and the Newtonian description is that, in particular, in general relativity, when a light ray comes near another body, it will feel the presence of gravity. Whereas in Newtonian mechanics, of course, it does not, because a light has no mass, and so the force is zero because the force is proportional to the product of the two masses. So one of the earliest prediction of general relativity is that if you observe, for instance, if this is the sun, and you observe from some perspective here on Earth, you observe a star that turns out to be just on the side of the sun, you will see the star not in the actual direction where it is located, but in an apparent direction which is slightly different. It differs by about 1.5 arcseconds if the star is just on the edge of the sun. And as you probably know, this was the first effect to actually confirm general relativity. Eddington in 1919 took advantage of a solar eclipse, a total solar eclipse, to look at the position of the stars just behind the sun, or just on the side of the sun, during the day when the sun was in the way, and compare these positions with the positions without the sun, and found that indeed the position differed by about 1.5 arcseconds. So these trajectories followed by the sun are called null geodetics. They correspond to certain specific trajectories on space-time. Another prediction of general relativity, which Einstein himself didn't like, but it turns out it was true nevertheless, is that if you manage to take a certain mass and compact it sufficiently to a sufficiently smaller size, then the distortion of gravity will become so strong that you will create a singularity. You will create a point in space-time where the deformation of space-time, the curvature of space-time will be infinite, and you will end up with a singularity. And the singularity, together with, will create what's called an event horizon, that is a region of space which becomes decoupled from the rest of the universe, in which you can see, and this region is called a horizon. So this is just a very, very brief summary of general relativity. The reason I want to say that is to explain the main feature of the EHT images, which is the presence of what is called a shadow. So to see where the shadow exists, here is the question we are trying to ask is, suppose you have a screen here. You're recording an image on this screen, the green line. And you have a black hole. You're looking in the direction of a black hole, right? M87, for instance. And you ask yourself, so what am I going to see on my screen? So to answer that question, you ask yourself, okay, I'm going to take every pixel on my screen, and I'm going to ask myself where the light rays that enter that pixel are coming from. Okay. So this is called ray tracing, because you follow the light ray, but you follow it the other way around. You follow it from the screen to its origin rather than from its origin to the screen. And so, for instance, this position on the screen at the top here, you ask yourself, where does this light ray come from? So in order to enter the screen, it has to come perpendicular to the screen, and then you start following it. And you basically find that this light ray, because of the same effect that I showed earlier on the previous screen, it's coming not exactly from the direction perpendicular to the screen, but it follows a certain geodetic, and so that light ray actually follows that trajectory. Right? So you're seeing the emission that doesn't come from right in front of you, but somewhere on a curved path like this. And as you consider light rays that are that have an impact parameter compared to the black hole smaller and smaller, then the effect is increasingly large. The deflection that this light ray has followed is larger and larger. So for instance, if you see one of these light rays here, naively you would think that it's coming from right in front of you, but in fact you're seeing a completely different direction because of the curvature of space-time around the black hole. Right? So the first thing that this tells us is that the image is going to look weird, right? It's not going to, the presence of the black hole is going to have a strong effect on the image that we are going to see. Right? This is unavoidable. But the other effect is that there happens a time, which is marked by the red trajectory here, when in fact this light ray is going to intersect the black hole itself. So this light ray that's marked in red, if you follow it and you follow the geodetics, it's going to end up within the black hole. So in fact, you can separate two regions on your screen. One of the region, which is marked by all the green lines here, are light rays that actually end up at infinity. They came from, they follow a path and go to infinity somewhere. So this one, the most internal one, makes a full turn almost around the black hole, but it continues to infinity. Whereas the ones that are marked in black, or starting with the one that's marked in red, actually end up in the black hole. So these trajectories are going to be a lot shorter, right? They have a finite size and end up inside of the black hole. Okay? And this is what defines the shadow, what's called a shadow. So the shadow is a region on your screen where you're looking at rays that actually end up inside of the black hole. You're looking at light rays that have a finite length and end up inside of the black hole. Okay? And so the next thing you can ask is, so how big is this thing? Right? How big is this region? Well, naively, you could think perhaps that it's the size, the black disk here indicates the size of the black hole, the Schwarzschild radius of the black hole. I'm assuming for the moment this is a Schwarzschild black hole, no rotation. So you could say, okay, well, any light ray that intersects the black hole on a straight line will be in that situation. Well, that's true, but it turns out that the region, that region is actually larger than the size of the black hole. And the reason it's larger is because even these light rays here, which if gravity was not present would go straight and would miss the black hole, because the space-time is curved near the black hole, they will curve and fall inside of the black hole. Right? So the shadow size is actually larger than the angular size of the Schwarzschild radius. Okay? And in fact, you can define a sphere or a circle in that diagram, which I marked in blue here, which precisely is the border between what will and what won't fall inside of the black hole. Any light ray, you can see that every black light ray that crosses this blue border falls into the black hole, including the red one. Right? The red one crosses that circle and falls into the black hole. But the last green one, which you can barely see because it's just outside of this, you can still see it here, and it goes out. So if a light ray crosses that sphere, it will fall into the black hole. If it doesn't cross that sphere, it won't. Okay? So that region here is called, is a separation between the two regions. It is significantly larger. In the case of Schwarzschild, it's actually exactly 1.5 times larger than the Schwarzschild radius. And the other thing is the shadow is even bigger than this sphere, right? It's about another factor of 1.5 times bigger than this sphere. Right? Because again, these light rays, they will cross that blue region, but on a curved path, right? So the shadow is even bigger than this. So in the end, you have three different regions. One is two different radii to consider. The first one is the event horizon. So the Schwarzschild radius, which is in Schwarzschild metric 2gm over c squared. Then you have this sphere here, which is called a photon sphere, which is that blue sphere that I drew in the previous diagram, which is 1.5 times bigger, which is the region where if you cross here, the photon is going to end up inside of the singularity. And then you have sort of the image of that sphere seen from the observer, which is even larger, and which has in fact a radius of about 25 over 2.6 times the Schwarzschild radius, which is the size of the shadow, right? So what you see in the background here are, it's an animation where what they do is they draw light rays from the screen, from the right. They follow them, and they draw them in yellow. And if those light rays cross into the photon sphere, then they remove the drawing of that light ray, right? So what you are left with at the end, that gray region that you're left with at the end, which would contain all the light rays that do end up inside of the black hole, this here is precisely the shadow. Okay? Right. I hope I made it not less clear than before. So this means that if you look on the screen, your screen is separated in two regions. One region, which is, well, maybe it was better in the previous. One region, which is marked in gray here, are all the light rays that do cross inside of the photon sphere and end up in the black hole. And then you have the region outside of this here, which are light rays that do go to infinity. Okay? That curve, curve that separates those two regions is marked by C here, and it's called a critical curve. It's a circle in the case of a Schwarzschild black hole, but it's not a circle in the case of a rotating black hole. In the case of a curved black hole, it's not a sphere. It's a more complicated shape like this. This was actually worked out quite a long time ago. And it's a kind of a D letter shape. Right? And these are different examples of this curve, drawn in different colors. This is if you see it at a fairly small inclination. This is if you see it at a larger inclination. And the different curves show all black holes from a almost maximally rotating black hole in red to a Schwarzschild black hole in blue. Right. So this curve, the size changes a little bit if you have rotation, if you have angular momentum. It's a small correction. It makes, if you have angular momentum, it makes this region a little bit smaller. But it's a small correction, and the main term is actually the mass. And then the shape, so that this is the radius of this region. And then the shape, if you see it here, actually it goes independently of the inclination. It's a circle if it's a Schwarzschild black hole, and it becomes more and more a D letter if it's a curved black hole.
Excuse me.
Yeah.
This inclination is the inclination of what?
It's the inclination of, so 0 would be
Rotation, right?
yes. So 0, the angular momentum of the black hole would point right at you. Okay. And 90 degrees, the angular momentum vector would be exactly perpendicular on the plane of the sky, perpendicular to the line. Okay, so this is more or less seen from above with the black hole black hole angular momentum pointing at you, and this is about like this. Okay. So for that shadow to have a shape like this, noticeably not circular, it has to be a large angular momentum, and it has to be seen more or less perpendicular to the angular momentum. All right, so let me now say what does that imply for the image. Well, this is kind of a general thing, but the image, how is the image formed? Well, to form an image, you observe at your screen here, and you observe certain directions, right? And what do you see? Well, you see if you follow a light ray, right? So you have to solve, for each light ray, you have to solve the equation of transfer, right? The additive transfer equation. So we are in a situation where the emission is optically thin, so we can ignore this last term here. So just as you integrate over the depths of your light ray, for each little bit of the light ray, you have to add the source function at this position. Right? So for instance, you follow this light ray here, okay? And you start, for each little delta x over the light ray, you add delta x times the source function, or delta tau times the source function from the light ray. Okay? And so what's happening is, if you have a light ray like this one, which do end up in the black hole, you're only going to integrate over that part of the light ray, right? So it's going to be a fairly short integration. Whereas if you integrate over a light ray that goes here, then you integrate over the light ray to infinity. So it's going to be a longer light ray. And so the result of this is that you see a shadow, right? You see the region at the center, the region that contains all the light rays that pass close enough to the black hole to fall into the black hole. Those are going to be relatively short integrations, and you're going to see less emission, right? So you're going to see a dark region, or not dark, but a darker region near the center. Whereas if you look outside of this, these light rays go to infinity, so you're going to see a brighter region. Okay? So that's the reason why we see this dark region in the center. This is the shadow. By the way, this is also, this equation combined with the geodetics is also responsible of the, this is a nice simulation that was made by NASA of a black hole where, as we all know, you see behind the black hole, this is a disk seen almost exactly edge on, but this region here is a part of the disk that's behind, right? Because like rays are curved. And the reason is exactly this, right? If you follow one light ray, it goes around the black hole. So along that same light ray, you're going to see material that's in front here, but you're also going to see material that's in the back. So you're going to see an image also of the back of the black hole. So this really comes from combining the size of these light rays, of these geodesics, and the radiative transfer equation. Okay. Please feel free to interrupt me if you have any questions. So this explains why we see a darker region at the center. But that's not it. In addition to that darker region at the center, we see this bright ring around it. So now what I want to try to explain is where that bright ring is coming from. And to do that, we have to ask another question, which is what happens if we consider a light ray that impacts the screen exactly on the critical curve. So remember, the critical curve separates the region inside, which are rays that go to inside of the black hole, from rays outside that go to infinity. Right? So what happens to a light ray if it hits right on that critical curve? Well, as you can imagine, it's not going inside, because to get inside, it would have to hit just a little bit inside of that curve, and it's not going to infinity either, because it would have to hit outside to go to infinity. So what does it do? Well, it turns out this photon is going to stay in orbit around the black hole. So in the case of a Schwarzschild black hole, these orbits are circles, right? The photon just stays orbiting the black hole in the circle with a radius, which is equal to 1.5 times the size of the Schwarzschild radius. Okay? If it's a Kerr black hole, it's a lot more complicated. In fact, in a Kerr black hole, that curve is not even always at the same distance from the center of the black hole. So There are different radii, but it turns out at any radius, the photon is going to stay on orbits that describe a sphere around the black hole. They are not circular orbits, they are kind of these complicated orbits like those that are drawn here. But they do stay at a constant radius on the surface of the sphere. So those photons are going to stay there forever. It turns out these orbits, these spherical orbits, are unstable in the sense that if you're just outside or just inside, then you're not going to go back to these orbits. You're going to diverge from these orbits, either to infinity if you're just outside, or inside of the black hole if you're just inside. So those that are just inside, we don't care about those because they are going to end up in the black hole, and they're never going to get it. But what is interesting is to look at the orbits that have an impact parameter just outside of that critical curve. So what we're going to look at now are orbits that are light rays that impact just outside of these curves. And to explain that, there's a beautiful simulation that was made by colleagues of the IAG-USP, which is shown here. So the first, let me pause it. So it's too late. Sorry. Okay, so let me, before we start. So here's the screen. Okay? Here's the black hole. This is the drawing of the perturbation of space-time due to the black hole. And here is the photon sphere. So that region that, by the way, it's called a photon sphere precisely because of this, because photons stay in orbit on that sphere. That's why it's called this. Okay, so now the photons that are the light rays that are going to end up on the screen can be separated into artificially. In reality, the screen just sees what it sees, but artificially you can separate it into different the superposition of different images. So the first image is going to be the image of photons that are produced in the back of the black hole, and that just rotate a little or follow the trajectories around the black hole before they end up on the screen. But just they are just affected in like that light ray around the sun. Right? It just goes around and ends up on the screen. Okay? So we're going to call these the n equal to 1 case. So these are photons that start here, they are deviated a little bit, and they end up on the screen. Okay? And they are going to produce an image on the screen, which is going to look like this. So it's going to be the image of what's behind the black hole, and a little bit focused towards us. And then you have a second image, which comes from material that's in front of the black hole, and where the light rays go half a turn around the black hole before coming to us. Okay? So we're going to call that n equal to 1. And then you have a third image, which is material that's in the back again of the black hole, but the photons, instead of going directly to the screen, they do one turn around the black hole before going to the screen. And then you have n equal 3, 4, 5, 6, and to infinity. Right? And if you look at the final image, it's going to be the superposition of all these sub-images. So this is what you get. You get the n equal to 0 image, which is just the photons that kind of directly come to you, just focused a little bit like the black hole. N equal 1, which are the ones that do one half turn. N equal 2, they do one turn. 3, 4, 5, 6, 7, etc. Okay? Up to infinity, and the final image is the sum of all of this. Well, it turns out that the first image, the n equal to 0, sorry, this one, is kind of looks like the actual distribution if you didn't have the black hole. Okay? Just with some gravitational lensing, but not a lot. But the n equal 1, 2, 3, etc., they are heavily lensed because they need to have exactly the right impact parameter to do exactly half a turn or one turn. So these are actually rings like this, and each ring is a little bit smaller than the previous one because for to do a full turn, you need to be a little bit closer to the critical curve than to do half a turn. So the impact parameter has to be a little bit smaller. So this ring is going to be just a little bit smaller than this one. And the brightness also goes down as you go from one ring to the next. Okay? But so the final image looks like this. You have sort of the image of what's really around the black hole, plus this ring, which is a superposition of an infinity of rings, but all are rings, very narrow rings. And in fact, these kind of images where you see some diffuse emission plus a very clearly defined ring is present in all the simulations. This is just a toy simulation, but these are real simulations. The LMHD simulation, where they put a plasma around the black hole, they describe the plasma in a certain way, they suppose a certain mass and a certain what's it called, angular momentum for the black hole, and they produce an image. Okay? And these are the images, and you can see in all of them, you see some diffuse emission and a very well-defined ring. Okay? And those, by the way, are different, very different black holes. This is a short-shaped black hole, no spin. This is a black hole with a fairly large spin, rotating in the same direction as the disk around the black hole. This is a black hole with the same spin, but opposite to the rotation of this is a counter-rotating black hole. And these are different, sane and mad. I'm going to speak a bit more about this later. These are different descriptions of the plasma, of the gas around the black hole. So they're all very different images, and yet they all produce the same signature, which is a ring and a shadow at the center, a ring and a dark region at the center. These features are actually very universal. If you have a black hole, you're going to see a ring and you're going to see a shadow at the center. So depending who you ask, it's good news or it's bad news. It's good news if what you're interested in are black holes and gravity around black holes. Because what this means is it doesn't really matter what the true distribution of the gas around the black hole is, or what kind of physics you need to describe that gas. You're always going to see the shadow, and you're going always to see the ring. Right? So if what you're interested in is seeing that ring or that shadow, then that's what you care about. And you might be interested in this because it tells you about the mass of the black hole, and if you have a good enough image, it could tell you something about the angular momentum. And in fact, in our two images, M87 and Sgr A, we did measure the size of this ring and to make sure that this corresponds to what you expect, given the mass. So that if that's what you want to do, it's good news. But if what you want to do is understand the gas around the black hole, then it's very bad news. Because these three models that I showed earlier, if you then take those models and you produce a synthetic image of what you will see with the Event Horizon Telescope for these models, so you add noise and you integrate the resolution to the resolution of the Horizon Telescope, these are the images that you obtain. They're all pretty much identical. And they're all the same as the image that we obtained, that we measured of M87. In other words, the fact that these features are so universal that you will always see a ring and you will always see a shadow makes it very hard to distinguish between different models. Here we have three models, very different black hole, very different plasma around the black hole, and all of these models are perfectly compatible with the image that we see. So if what you want to understand is, how the surrounding of a black hole works, then it's really bad news. In fact, the only thing that we can really say from these images is the mass of the black hole, because this is the size of the ring. Right? If you measure the size of the ring, you get the mass of the black hole. But does it have a spin or not? Well, really, we don't see. We can't really tell if it's a perfect circle or a D letter, so we can't tell. We don't even tell where the emission really comes from. Is the emission dominated by a disk of material around the black hole, or is it a jet or even a counterjet that is producing all these photons? We don't know, because it doesn't matter where they come from. Wherever they come from, they're going to form this ring anyway. So, of course, it doesn't tell us about the strengths of the magnetic field. It tells the magnetic field. So there's a lot of things that we can't tell from this image. And as an example, for instance, from this image, if we try to reconstruct the accretion rate on the black hole, which is one of the most fundamental parameters you might want to there are 4 orders of magnitude, so 3 orders of magnitude uncertainty on these deduced. So does it mean we are in a lost situation? Well, not quite. Because what we can do also, and this is actually what Shelley has been specializing on, is you can look at polarimetry. You can decompose the light into its 2 polarization, either linear or circular, and obtain images of the black hole in polarized light. And so these are the images that we obtained from the same data as before. Here the thick marks, or these kind of hairy things, here they indicate the direction of the electric field associated with the incident radiation. So you can see that the electric field is kind of azimutally distributed. It's more or less constant throughout. These are the 4 days of observation, so you can see that the structure doesn't change much. It's always more or less the same. And this already tells us something. It tells us something about the topology of the magnetic field. In particular, it tells us that, so these are 3 very basic toy models, where the magnetic field is distributed in a toroidal way. That is, the magnetic field is going around the black hole like this. This one is a radial magnetic field, so it's pointing out of the black hole, and this one is a vertical, so it's kind of in the material around the black hole, but pointing in the same direction as the spin of the black hole. And these are the predictions that you get. So this, you perhaps can't see that, but this is immediately discarded because this produces electric vectors that are radial in this image, exactly perpendicular to what we actually observe. So what this means is that the magnetic field around the black hole is somewhere a combination of these 2 effects. Right? So it has a very significant colloidal component and probably no or very little toroidal component. Do I see something?
Yes.
Okay. So just to quantify this, we define a number of parameters out of the polarized image. This is the net polarization. This is the mean polarization over the entire image. And there's these other quantities here that are kind of moments, azimutally average moments of the images, which turned out to be very, very useful. So these quantities you can obtain from the polarized image, and you can also obtain for models that you are interested in. So what the EHT did was the EHT collaboration to analyze these images. They produced about 60,000 different images that correspond to many different snapshots of different models, exploring the mass of the black hole, the angular momentum of the black hole, the description of the plasma, etc., etc. So, and as we said, we saw earlier, a lot of these images pass the test of the total intensity map. The initial image of the black hole without the polarimetry, we can explain it with many different of these theoretical models. But now all these theoretical models were compared to the polarimetric information, okay, to see which one passed and which one did not. So here's for an example of this. So these are histograms of the number of images, theoretical images, as a function of, for instance, the net polarization, one of these parameters that I showed earlier, or the image average polarization. And all of these histograms show different kinds of models. So essentially there are 2 families of models. One family is called MAD. MAD stands for magnetically arrested disks. And these are models where magnetic field is important. The magnetic field intensity is fairly high. And then the other category are the sane models. Sane stands for standard and normal evolution. And those are models with much lower magnetic field. And so those are histograms for each of these 2 categories of models, what you would expect, for instance, in terms of linear polarization. As you can see, the sane models produce fairly low net linear polarization, whereas the MAD models produce larger linear polarization. It makes sense because they are more magnetic, they have higher magnetic fields. Right? And in terms of this average image average polarization. These are the histograms. And then the blue region here shows the measurements, where the actual EHD images stand in terms of these values. And you can see, for instance, here it's very clear, right? The true value falls right where the sane models are not, right? And the same is kind of true here, and it's even more true if you look at these other parameters, these beta parameters that I was showing earlier. This is the same representation. As you can see, the true measurements kind of want to avoid where the sane models are. So what this means is that of all the models that could reproduce the integrated intensity image of M87, only the ones that are of type MAD, that have fairly high magnetic fields, actually reproduce the polarimetric information. So this polarimetric information was actually much more important than the non-polarized image to study the physics of the plasma around the black hole. Last week, in fact on Tuesday or Wednesday, I don't remember, last week, a new paper came out from the collaboration looking at circular polarization. So those are very neat images. These are the same as I showed earlier. These are images where the tick marks also show the linear polarization, but you can see there are some ellipses around here, and the ellipses show the circular component of the polarization. Circular polarization is really hard. It's very, very hard to detect. And in fact, the only conclusion of the paper is that we detect some level of circular polarization. We don't quite know more than this, but the same thing happens. This is the same representation. Again, this is in terms of our circular polarization, the region that's allowed by the data. And you can see once again, the same thing happens, that the same models get discovered. So all this polarization work enabled us to sort of nail down a better description of the plasma. And this has important implications for the rest of the physics around the black hole. For instance, this is the accretion rate. So as I said earlier, there's 3 orders of magnitude uncertainty on the accretion rate if you take only the total integrated image. But if you include polarimetry, this restricts the range to about this value, which is still about an order of magnitude wide, but it improves the situation by 2 orders of magnitude to incorporate polarization. So in summary, the integrated light image is mostly sensitive to the presence of a rim and a shadow. And where the emission comes from, how it is produced, it has fairly little impact on the rim. But the polarization image is what encodes the physics of the gas around the black hole. And by obtaining this data, we can say more about the characteristics of the black hole. So this is basically my last slide. I just want to, well, I have 2 still. So these regions, the regions around black holes, they are very dynamic region. The gas is very turbulent. So if you take an image of a black hole, or you have an image of that black hole at that time, you take another image of the same black hole 2 weeks later or 2 years later, you might not obtain this. So this is, for instance, a simulation that shows a certain black hole. And you can see if you take snapshots of these animation, you get different images at different time. So one of the things that we want to do in the future is expand what we've done by taking more images of these black holes to follow how they change. Everything that I've showed you and everything that's been published so far was obtained from the one campaign in 2017, the first campaign of the Event Horizon Telescope. But there's been observations in 2018, 2021, 2023 that incorporated more stations, more telescopes. Now we are up to 11 stations, 9 different sites on Earth. And the bandwidth has also increased, so the images will have higher resolution. The bandwidths are also more separated, so polarization should also become better. So we have a lot of data that could be, that will hopefully be published in a not too distant future. I don't want to mention this, and I didn't mention it, but there are other targets that have been observed with the EHT other AGNs, active galactic nuclei. But for all of these others, this is a complete list here with the name of the source and who published them in what year. They're all too far, and we cannot see the shadow, we cannot see the general relativistic effect. But these are very interesting to understand the formation and collimation of the jets that come from these objects. So these are images with unprecedented angular resolution of these sources, and they are all very interesting in itself. And just this, I promise this is my last slide. This is sort of a more distant future. The idea is to expand the Event Horizon Telescope and to morph it into what is called a next generation Event Horizon Telescope that will include, in addition to the existing telescopes, about a dozen other telescopes around the globe that where some of them are just, for instance, the one here in Africa. It will be put where it can be put. There's there are not very many high mountains in Africa, but many others will be put in places that are particularly useful to obtain better images. So this could be an entirely different talk. I don't want to enter into the details, but this will allow us to obtain better images where we see at the same time, for instance, the black hole itself or the shadow of the black hole and the formation of the jet to relate these two scales that we cannot relate at the moment. And just so I mention it, Yama here, or Yama, I don't know how you call it here, is included into those plans to the next generation EH. And I'm going to stop here.
Thank you, Professor. I think I learned a lot in a very short period of time. And we have time for a few questions, if anybody in the audience has any questions.
If I want to improve the angular resolution of the telescope, what should I do? To improve the number, to increase the number of antennas, is it?
No, well, that will improve the sensitivity and the UV coverage, so it will improve the quality of the image. But there's only, the resolution goes as lambda over d, where lambda is the wavelength of the side of this telescope. So we're already at the limit of the size of the Earth. So without going to satellites, we cannot make d larger. So the only thing we can do if we don't want to go to satellite is make lambda shorter. And this is part of what's actually planned with the NG-EHT that we are currently observing at 1 millimeter, 1.2 millimeters, or 230 gigahertz. And this will go up to 345 gigahertz, or 0.8 millimeters. So it will gain about 50% angular resolution. But if you want to gain more angular resolution, and this is also being discussed, then you have no choice but go on satellites. You have to put radio telescopes on satellites orbiting here.
Does anyone have any other questions?
So thank you for the presentation. I was just wondering what may cause the circular polarization in the surrounds of black holes, because well, you know, the dust polarization, the synchrotron polarization is all linear polarization.
Exactly. So it's actually not, we think that it's not actually intrinsic, that it's what is called Faraday conversion. Thank you. Faraday conversion. So it's the polarization intrinsically from it's all synchrotron radiation. So the polarization initially is linear, and then it goes through this ionized material to the surrounding, or internally within the region that's producing the emission. And here Faraday rotation and what's the name again?
Faraday conversion.
Conversion. Thank you. This Faraday conversion transforms some of that linear polarization into circular polarization. It's not an intrinsic. Thank you.
For the clear talk. So you're going to have the two others wavelengths with the next generation.
Yeah.
So besides resolution, of course, you can look at different scales. Also, you can separate these different models for the black hole from some information that will come from these different frequencies, this spectrum.
Yeah, so the main reason is really angular resolution. It's to increase angular resolution.